In this video, we're going to look at how to evaluate triple integrals on non-rectangular solids. So we saw in the previous video how we can evaluate an integral, a triple integral, on a rectangular box in 3-space. And that was just finding the sides of the box in terms of the x on the x and y and z axes, and then using those limits or those sides as the limits of integration. If we have a solid that we're integrating on that is not a box, we have to do a little bit more, just like we did with double integrals when we didn't have a rectangular region. Now we're not going to go through the development, but the definition of a triple integral remains the same. We would break up our solid into little boxes. We'd pick a point and we'd form a triple Riemann sum and then take a limit. In terms of how we go about actually computing a triple integral over a non-rectangular solid, there's no one way that always will work. It really depends on the region or on the solid itself. But I do want to talk quickly about a typical strategy to write our triple integral as an iterated integral. Right. Right, so if we have a triple integral, in order to compute it, we want to write it as an iterated integral and compute this. But the hard part of this problem is to be able to actually write it as this iterated integral. And so here are some basic steps of how we can approach almost every triple integral, and that it will work. So the first step is to find a lower surface which maybe I'll call h1xy, and an upper surface which I might call h2 of xy, for our solid S. Right. So this is really no different than what you might do for other types of integrals. If you're looking at the integral of finding the area between two curves in a single variable situation, the first thing you're probably going to do is figure out what is the upper curve and what is the lower curve, sort of bounding the region that you're taking the area of. And did the same thing with double integrals. When we were integrating over a triangle, for example, we had to come up with bounds for x and y, and we looked at the upper curve and the lower curve and the left and right curve if we're looking on the x side. And so we're doing the same thing here, but the key is here we want to look at z first and find sort of the upper curve or the upper surface and lower surface. And these surfaces will typically involve both variables x and y. Right? And so once we find that the surface lies, but once we find that our solid lies between these two surfaces, then what we can do is we can look at the projection of the solid in the xy plane. And our first step has taken care of the z dimension of the solid. So now we're going to focus on the xy dimensions, which we can look at just in the xy plane. So we look in that projection. We're just talking about the shadow of the surface of the solid in that plane. And in the xy plane, we can find the lower curve. I'll call it y equals g1 of x. And an upper curve for that region. I'll call the upper, we have an upper curve, which I'll call y equals g2 of x, for that region, for that projection into the xy plane. All right, so we've handled the z direction, and we've handled the y direction now by looking at the upper and lower curves. And then we can find values x equal a and x equal b. So these are constants that serve as a boundary for the region, given our choice of upper and lower curves for y. Okay. Right. So in short, this strategy says find bounds on z, then find bounds on y, and then find bounds on x. And most of the time, this strategy works really nicely with integrals. However, depending on what this solid S actually is, it might be necessary to find bounds on y first. That would involve x and z, and then find values of z for that involve just x, and then find the values of x, the boundary in that direction. So this is not the only way to do this, but usually there's one dimension where the solid is between this surface and this surface, and if those are both z surfaces, z equals some functions of x and y, then we're going to apply the strategy here. If we have between surfaces y equals some combination of x and z, then we might kind of exchange the letters y and z in this strategy. However, once we have this strategy, once we have these limits, we have all the information we need to write down the iterated integral that we need to compute. Right? So given the choices of curves and surfaces that we just found, the triple integral of a function f x y z dv would be computed as the following iterated integral: a to b, g1 of x to g2 of x. Right, those are the upper and lower curves in the xy plane. And then here we would have h1 of x1 y1 or xy and h2 of xy. These were our upper and lower surfaces for our region. And this is dz, dy, dx. Right, so typically this is the approach that we would take here. And like I said, if we want to change, if the region is more naturally defined by being between curves y equals functions of x and z, then we would find those first and then look in the xz plane and find the projection there. Right? So let's look at an example. Okay. So let's say we wanted to evaluate the triple integral over a region S of the function z, right, dv, where S is the tetrahedron bounded by the following curves. Right, so it's going to be bounded by x equals 0, y equals 0, z equals 0, so the three coordinate planes, and the plane x plus y plus z equals 1. So in order to do the strategy that we laid out a little bit ago, it is kind of helpful to see what this solid looks like. And so the four planes here, the first three are just the coordinate planes: the xy plane, the yz plane, the xz plane, and the xy plane in order. And x plus y plus z equals 1 is going to be the plane that intersects each of the three axes at the 1 unit mark. Right? And so I'm going to have the point here and here and here. So these are the points 1, 0, 0, 0, 1, 0, and 0, 0, 1. We can see all three of those points are on this plane. And so when the plane will go through these 3 points, and so the tetrahedron that we're considering is this tetrahedron right here. Right, so it's cornered in there at the origin, and then bounded on top by this plane x plus y plus z equal 1. Right, so we can see this three-dimensional figure. All right, so I'm going to start this before we try to integrate. We're just going to write down all the boundaries of this particular solid, and so. On the boundaries, we need first lower and upper surfaces. So we notice that the lower surface, the bottom of this tetrahedron is just the plane z equals 0. It's the xy plane. Everything lies above that. And everything lies below the plane x plus y plus z equals 1, which if I solve for z, is z equals 1 minus x minus y. So this is the lower surface and the upper surface that describes this particular solid. Okay. The next step is to look at the projection of this solid in the xy plane. And when we do that, we notice that it does intersect the x and y axes at the point 1 on each axis. And of course, it hits the origin. And so this particular projection onto the xy plane will just be this particular region, this triangle. Okay. And we know this third side of the triangle over here is going to have an equation of negative x plus 1. Right? It has a slope of negative x and a y-intercept of 1. Okay. And so when we go now to look at the boundaries of this region, we want to look at the boundaries of y. So y is going to go from 0 down to at the x-axis, and that's our lower curve. Our upper curve here is the line we just indicated, so y equals 1 minus x. Right? And so y lives in that range. And then x will go from 0 to 1. Right? We have x equals 0 here. We have x equal 1 here. So along the x-axis, this surface lives between x equals 0 and x equals 1. Right? And so these three sets of boundaries that we just identified, and pretty easy to identify them from the picture, these are going to be the limits of our triple iterated integral. So our triple integral over S of dz, using the boundaries that we just found for our solid, we're going to have the integral from 0 to 1, 0 to 1 minus x, and 0 to 1 minus x minus y of our function z, and then the order of integration is dz, dy, dx. Right? And so we just have to compute this iterated integral. Right? So as always, we will start with the innermost integral, and we have to differentiate z with respect to z. So we have 1/2 z squared evaluated from 0 to 1 minus x minus y. Although we don't have to, I'm going to go ahead and pull that 1/2 out front. And we can bring it out of all of the integrals since it is a constant. And then I'm going to evaluate z squared at these values. So I'm going to have 1 minus x minus y quantity squared minus 0. Right? So we have the integral of 1 minus x minus y quantity squared, the double integral of that, dy dx. Right? So now we'll compute the second integral. Right? Now, you might feel that you want to square out this term first and get a nice polynomial before we integrate. But it turns out that we don't have to. Remember, we're just integrating one variable at a time. And so we're thinking of this as a function of y. Right? And so when we integrate this, it's just a really simple u substitution. So I might make u as 1 minus x minus y. Du is just going to be negative dy. And so when we do this, we'll just have to include a negative sign with the integration. And so the antiderivative of this function is just going to be negative, and that comes from the substitution. 1 minus x minus y cubed all over 3. Right? And that'll be from 0 to 1 minus x. Right? All right, so I'm going to bring the negative and the 3 in the denominator outside the integral, so to combine it with the constant. So we're going to have negative 1/6 integral 0 to 1. And then we evaluate, so I'm going to have 1 minus x minus, and then I'm going to replace y with 1 minus x. So I'm going to have 1 plus x, all of that cubed, minus 1 minus x minus 0 cubed. All right, so now what we notice is that this first term here is 0, and this middle term, the second term rather, will be negative. So we're just going to have a single term integral of a negative number. So I'm going to bring out that negative out to the constant out front, and it's going to become a positive 1/6. Integral 0 to 1 of 1 minus x quantity cubed. All right, so we have to compute this relatively simple integral now. All right, so we have 1/6. The antiderivative here is going to be 1 minus x to the 4th over 4. And then we do have to account for that being negative x there. So another u substitution like before will mean we have a negative that we have to introduce here. And we'll evaluate from 0 to 1. So I'm going to get negative 1/6 times, we evaluate at 1, we're going to get 0, minus, when x is 0, we just get 1/4. And so I get negative 1/6 times negative 1/4, which is positive 1/24. Right? So this is the value of this particular triple integral. So let's look at one more example where we have to compute a triple integral. In this case, let's say we want to find the volume of a tetrahedron bounded by the plane x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So the first thing we have to determine is how we use a triple integral to compute a volume. And if you remember back to when we did double integrals, we were able to use double integrals to compute an area by integrating the function 1 over that particular region. And in that case, that made intuitive sense, because if you take a region, like say you take a rectangle on the plane and you want to know what the area of the rectangle is, if you raise that rectangle up 1 unit and form a solid with height 1, numerically that volume in that area are the same. The units are different, one's square units and one's cubed units. But if you just focus on the numerical value, if the area of that rectangle was 12 square units, then the volume of that box of height 1 will also be 12, now cubic units, but the numerical value 12 is the same. So likewise here, if we extend this to 3 dimensions, if I want the volume of a surface, then what we can do is evaluate the triple integral of the function 1 over that surface, and that will compute the volume. All right, this one's not as intuitive because we have to think about a 4-dimensional version of volume that we're then making that 4th dimension 1 to have the same numerical value as our volume, and that's just something we can't visualize. But it really is analogous to what we did with double integrals and integrating the function 1 to find the area. Right, so that's going to be our goal in this problem. What we have to do, we're going to integrate the function f of x, y, z equals 1 over S, which is the tetrahedron described above. Okay. And so, just like in the previous example, our first thing that we need to determine to compute this integral is to find our boundaries. And so in this case, in 3 space, it's a little bit harder to draw this picture. But we know 2 of these bounding equations involve z. And so we know we have a lower bound of z equals 0. And the upper surface is going to be the other plane, which will be z equals 2 minus x minus 2y. right? So we don't really need the picture. In this case, we know the two equations of the boundaries that involve z are going to be our top and our bottom. To find our boundaries for y, it is instructive to have an xy plane and draw this picture here. So I'm going to draw this down here in the corner. Our three curves that are going to bound our region, we do have x equals 0, which is the y-axis. We have the line x equals 2y. Now, x equal 2y in this context is actually a plane. But remember, we're looking at projecting our surface down to the xy plane. And so if I take the plane x equals 2y and I project it onto the xy plane, it becomes the line x equals 2y. Or as we might call it, y equals 1/2 x. So y equal 1/2 x actually goes through the origin, and it has a slope of 1/2. So it might look something like this. Right? And I'll just point out this is coming from x equals 2y, that plane being projected down into the xy plane. Right? Now the other boundary for y comes from the plane x plus 2y plus z equals 2. And remember, we're projecting into the xy plane, which means we're setting z equal to 0. So when we set z equal to 0, this other plane, x plus 2y plus z equals 2, that should equal 2. This variable is going to be equal to 0 in the xy plane. So we simply get x plus 2y equals 2. And notice that this is, in the xy plane, a line. In fact, it's going to be y equals negative 1/2 x plus 1. And so we know that has a y-intercept of 1. So up here is a 1. And it has a slope of negative 1/2. So it looks something like this. And so our region in the xy plane is this triangle here. Right? And so when we look at this, we can easily see the boundaries of y. We see the lower curve for y is 1/2 x, and the upper curve for y is negative 1/2 x plus 1, or 1 minus 1/2 x. I forgot the x. So negative 1/2 x plus 1, or 1 minus 1/2 x. Right? The last step is to find the values on the for the x. All right, so notice that this region does start at x equals 0. That was one of our curves. We need the intersection point here, whatever the x value of that point is. And it's not terribly difficult to see from the equations that is going to be x equals 1. Right? If you don't see that just by looking at the equations, you can set 1/2 x and negative 1/2 x plus 1 equal to each other, and you pretty quickly get the equation x equals 1 out of that. And so our boundary is going to be from x equals 0 to x equal 1. Right? And so now we have our function, the function 1, and we have our three boundaries for z, y, and x respectively. So now we can compute an iterated integral. Okay, so our volume is going to be the integral from 0 to 1 of the integral from x over 2 to 1 minus x over 2 of the integral 0 to 2 minus x minus 2y of the function 1 dz dy dx. All right, so integrating with respect to z, we just get the variable z, we evaluate at the endpoints, and so we get the function 2 minus x minus 2y. Right, this one always comes for free. And now we have to integrate in terms of y. And so we have an antiderivative of 2y minus xy minus y squared. And this is going to be evaluated from x over 2 to 1 minus x over 2. All right, and so I'm going to let you do the algebra on this one, but we're going to replace each of the y's in this expression with 1 minus x squared and with x over 2, and then subtract. And just to save some time of you watching me do basic algebra, we're just going to jump ahead to the simplified version of this, which is 1 minus 2x plus x squared. Right, so I will just mention here that there is algebra missing here. This is not obvious, but I have faith that you can do this algebra. All right, but then we get down to this point, and so we have x minus x squared plus x cubed over 3 from 0 to 1. And so we have 1 minus 1 plus 1/3, all minus 0. And so it looks like the volume of this tetrahedron is 1/3. Right? And so again, the hard part of this problem is not the integration, just like with all the others. It's getting the bounds set up properly so that we can actually compute the integration appropriately.